Alright, so welcome back to our stream here at OneClass. Again, my name is Joey. I'm going to be your math teacher for the session for the next hour and for the other hour slot at about 12 p.m. Noon Eastern time. So what we're doing here at OneClass, if you're tuning in for the first time, thank you so much for tuning in. What we're going to do today is we are going to, we've been going through this kind of journey of answering verified questions sent by students and basically people from all around the world, particularly subjects such as in chemistry and in math as well. So we've been compiling a bunch of questions, frequently asked questions in those subjects. And our goal here at OneClass and my job here today is to help verify those solutions. So we get many solutions for these frequently asked problems, but sometimes, not all the times, the solutions are either incorrect or they're missing something, or we can always improve on our solution. So that's here, and that's kind of my job here at OneClass. And what we're going to do is every time we answer a question, the format here is that I'll give you some time at home if you're tuning in through the live stream. You can kind of get some time to kind of think about the question and then see if you can kind of answer it on your own. And then what we're going to do is I'm going to walk you through the question, and then we'll compare it to our the solution that we found here at OneClass, and then to see if it matches as well. And if it doesn't match, then we can clear up any discrepancies on why it does not match, and we can then verify our solutions here. So hopefully, for those of you at home, you can find this topic of interest, just because they are kind of frequently asked questions asked at school. And so our goal here at OneClass is to provide the best solutions for our students here, obviously free of charge in terms of online material. And so our videos are very easily accessible on YouTube and whatnot. So a little bit about me before we start. Again, my name is Joey. I'm currently I'm going to be a secondary school teacher in Toronto, and I'll be teaching primarily subjects in chemistry, so in kind of secondary school science and in general science as well. I can also teach music, and hopefully I'm about to get my math teachable further down the road, probably in September. So that's kind of a little bit about myself. And yeah, without further ado, let's get started. We have another 10 questions for us to kind of do today, and we're going to be focusing a bit on the senior math level. So maybe in late algebra 2 to about late algebra 2 pre-calculus, and in the Canadian curriculum or the Ontario curriculum specifically, it's more so in grade 11 functions and grade 12 advanced functions as well. So let's get started on that. So what we have today, our first question of the day is, what is the graph of f of x equals? This is 100 times 0.7 to the power of x. So it's asking us, and you can help me. If you're tuning in for the first time again, feel free to say hi in the chat. But we have f of x equals 100 times 0.7 to the power of x. So we're asking, how do we graph this function? So take a moment to think about this. What kind of function is this? How do we graph it? What is the parent function? All these are great questions, and I'm going to give you a hint over here. The 0.7x, if I have a function to the power of x, this here is an exponential function. It's an exponential function, and this here, in this case, it would be because it's the base of the exponent. So the 0.7 here is less than 1. It's between 0 and 1 specifically. This function is actually a decreasing exponential function. So I'll give you those two pieces of information to work with. And then what you are going to do is what you have to do is, again, you're finding the intercepts. What else are you doing? You're finding the x and y intercepts if they have any, or there may be asymptotes in exponential function. Hint, there is. And we're going to try to sketch a graph using the pieces of information provided. So let's do that, and then we will. I'll give you about a minute to do that, and then we'll take it up. So give you a minute to do that. So we have here, this is f of x equals 0 times 0.7 to the power of x. So when we're looking at this this function here, we have a decreasing exponential function. So what does that look like? And I'll sketch that out. So if I have an increasing, remember our parent function here, if f of x equals, let's say 2 to the power of x, I would have something like this, right? And I have an increasing exponential function, and our horizontal asymptote here is at y equals 0, right? And then if I had something like this, if I had like maybe like half or 0.5 to the power of x, I would get like a decreasing function. So it'd come up and then it would decrease and it would head towards 0 here, right? So this here is my decreasing exponential function. So in this case, we have sort of the second case here, right? Because it's between 0 and 1, our base is between 0 and 1, we're going to have this second case here. So let's find, actually, let me not erase this first. Let me redraw that. And what we're going to do is we're going to solve for some properties of our function here. So let's solve for our x and y intercepts. So if I want to solve for my x-intercept, what I have to do is I have to set y to 0, right? So in order for me to do that, sorry, for my y-intercept, I'm setting x to 0. Sorry, my bad. Sorry, y to 0. So if I were to do that, I can sub in f at 0 equals 100 times 0.7. That's to the power of 0. I'm subbing in x for 0 here, right? And then this would give me my intercepts, right? So again, I have 0.7 to the power of 0 is simply just 1, right? So f of 0, or in this case, I say y would equal 100, right? Because of this entire thing, anything to the power of 0 is simply just 1, right? 100 times 1 here is 100. So my y would be equal to 0. So let's now solve for my x value in this case. So I'm going to set y to 0. So I'll set f of x to 0 here. So this would be 0 equals 100 to the power, 100 times 0.7 to the power of x. I can divide both sides by 100. So if I divide both sides by 100, I get 0 on this side equals 0.7 to the power of x. And then what I'm going to have to do is I'm going to have to use a logarithm for me to get to bring this power down, right? I'm going to have to take the log of both sides. So I'll have log of 0 equals log of 0.7 to the power of x. And what that logarithm does is I can bring this x down here to here, right? So I have log of 0 equals x log x times log 0.7. 0.7, and I can divide both sides by log 0.7 to get my x value, right? But if you can kind of tell now, log of 0 divided by log of 0.7 doesn't exist. And if you don't believe me, if you type in log of 0 into your calculator, you get something called a math error, right? So it doesn't matter what you divide log of 0 by, you're going to still get a math error. And that means we actually have no x-intercept in this case. This here is going to give us x here is DNE or does not exist, which means there's no x value here, which makes sense because there is a asymptote, right, at the x value, right? So if you look at all the x's here, this will never touch x here, which makes sense. And our y value would be 100. So let me just sketch this graph. I'm going to do a really rough sketch of this graph. And what we can do is we can use Desmos to kind of verify this. And the only things we have here is our y value, which is at 100 here. Or let me do this with more space. It's kind of cramped here. Let me do this over here. The only value we can really put is this 100 here, right? Is that y here is at 100? We know here this is our y-intercept, and basically we know it's a decreasing function, right? So from here, it's basically going to come up like this, and then it's going to drag slowly and decrease to 0, because we know this is a horizontal asymptote. This here as I'll say horizontal asymptote, or a infinite discontinuity, HA equals 0 here, right? So that's kind of all we know about our graph. If you wanted to check a point on this graph, you definitely can. Let's plug in the coordinate of x equals 1, and let's see our y value. So we have here f of x to kind of verify that it's that shape. So we have f of x equals 100 times 0.7 to the power of x. I'm going to plug in f of 1. So f at 1 would equal 100. And again, 1 is just some arbitrary value, right? I'm just figuring out at f at 1 per se, what is my value here, just to get a better sense of my graph and to prove that it is indeed decreasing. So this is 0.7 to the power of 1. 0.7 to the power of 1 is simply just 0.7. So f at 1 is 100 times 0.7. And the f at 1 would equal 70 here, right? So again, this point here would be 70, right? This at x equals 1 here, y would equal, this would equal 70 here. So it's gradually decreasing. If I put a really big number into this function here, let's say x equals 1,000, for example, I'm going to have 0.7 to the power of 1,000, which will give me a very, 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 very small number. And then, which makes my y a very, very small number. And that's kind of the goal here as well. So I'm going to get this kind of function here. This is the graph of f of x equals times 0.7 to the power of x. So this is kind of this final answer here. I'm going to see what they did for their solution. So this is f of x equals 100 times 0.7x. Value is less than 1, so therefore decreasing function. Good. So we know that. They set f of x equals y. They set, now let x equals 0, they set y equals 100 to the y-intercept, so they solve for this as well. And then, hence, since 0.7 times 0 equals 1, this doesn't really make sense here. I don't know what they're saying in this statement here. Because 0.7 times 0 is not 1, it's 0. And as x tends to positive infinity, y tends to 0. That's good. And as x tends to negative infinity, y tends to positive infinity. Therefore, f of x is a decreasing function having horizontal axis of y equals 0. That's good. Hence, the function is something like this. Okay, that's good. So this is a great solution. I don't know what they mean by this here. 0.7 times 0 equals 1. I don't know what they mean here, but I'm going to copy this and say that good solution and analysis. I am confused by this statement. Because 0.7 times 0 equals 0. Other than that, your solution is correct. So their graph here looks a lot like mine, right? I have here the y-intercept at 0, and then if you look at point 1 here, this here is almost at 70. So this here is a great solution. So a good solution. I sketched my graph as well. Again, I don't have I can only do so much with my sketching here. So this is going to be my solution for today. So this solution here is correct. And then this here was the exact same. But here I picked this question because this is the exact same question, so I might as well get rid of this question here. So it's the exact same as the previous question. So it's a good solution and an analysis. I am confused by because 0.7. So I'm basically just retyping the same thing equals 0. Other than that, good step by step. So it was just the exact same question. I just picked both of them because they were the exact same question, just to kind of get rid of these solutions out of the way. Okay, cool. And let's do, this is now number 2 now. So let's see here, how many extraneous solutions does the equation below have? So how many extraneous solutions? And let me just write this out. So I have 2m divided by 2m plus 3 minus 2m over 2m minus 3 equals 1. So again, we're solving for our extraneous solutions. So what does it mean when we talk about extraneous solutions? We're talking about kind of holes or discontinuities, specifically a removable discontinuity in our equation here. So take a moment to think about this. Again, this is a rational expression, right? We have a fraction. That has a 2m plus 3 as a denominator, and we have 2m minus 3, right? So we have to use something called lowest common denominator in our rational expression. So again, take a minute to think about this question, and then we will take it up together. Here. I don't like this m here. There you go. So we think about lowest common denominator. How do we combine both of these fractions to make sure that they have the same denominator? So if we're given this problem here, and I want to isolate for this m value here, what I'm going to have to do first is I'm going to have to put all these two terms here in a lowest common denominator. So this is here's 2m plus 3. This is 2m minus 3. I need them to be in the same denominator, which means I need to multiply this term by this term here. So I'm going to get something like this. So 2m plus 3 is going to be at the bottom. I'm going to multiply it by this lowest common denominator, because I need basically a similar term for both of these denominators, so I can combine the numerators, right? So this here would be 2m minus 3, and then at the top, for the top of this problem here, I'm going to get 2m multiplied by 2m, right? Because I have 2m here, and I need to multiply by this m here as well, because this m is part of this this fraction here. And similarly, what I'm going to have to do with this one here is I have 2m minus 3. I'm going to have to multiply that by 2m plus 3 to get the same denominator. And then I can do the exact same thing. It's 2m times 2m here. 2m times 2m. And that's going to equal 1, right? Here. And now I can simplify this equation here, right? I can simplify this equation. I can put them all into one kind of fraction. So I have here, this is simply just 2m plus 3, 2m minus 3, and I have 2m times 2m, which is 4m squared, and this here minus is 4m squared as well. So what I can do now is I can, let's see, this here will equal 1. And then what I'm going to have to do is, I'm giving this rational expression here. I kind of have a difference of squares at the bottom, because I have 2m plus 3, 2m minus 3. So I could rewrite this into something like this. So it'd be 2m squared, and then it'd be whatever 3 squared is. So this would be 4m squared minus 9 would be my difference of squares. Kind of a thing over here. 4m minus. Oh, hold up. I think I did the wrong thing. My bad. Sorry. I caught myself as a mistake. So give me a second. Let me rewind. So I am multiplying not by 2m here. This is not by 2m. I'm multiplying this term by 2m minus 3, right? This here is 2m minus 3, and this here is 2m plus 3. And the reason why I'm doing that is I'm basically multiplying by 1 here, right? These two terms divide out to 1, and these two terms are dividing out to 1. I'm not simply throwing 2m randomly over. So that's my fault. I multiplied the numerator instead of the denominator. Sorry about that. So I have this new term here. I'm going to do the distributive property. I have 2m times 2m here, which is 4m squared. 4m squared. And then 2m times minus 3 here is minus 6m here. Similarly, I have, this is going to be minus. And then this entire, it's subtracting this entire term, right? So this entire term is going to give me minus, so I'm going to put a little bracket here. This is, again, 4m squared minus, this is positive 6m. Positive 6m. So what I can do is I can then simplify this bracket into, this is 4m squared minus 6m Okay, it's simple. So this here is now minus 4m squared minus is minus again minus 6m here, right? I'm breaking down this bracket. I'm using this negative applies to all of this entire bracket here. So this here equals 1. And then I can see that 4m squared and 4m squared cancel out. Minus 6m is minus 12m, right? So you have minus 12m divided by 4m squared minus 9, right? And that's going to be my kind of equation here. So here equals 1. And then let's see, what else can I do with this variable here? I can simply just multiply the denominator to the other side, right? I'm isolating for my m here, right? So I have my negative 12m equals 1 times 4m squared minus 9. And then what I can do is I can bring this 12m to this side, right? To the right side to rearrange it to become a quadratic function here, right? So I have 4m squared. This will be plus 12m now minus 9 equals, or equals 1. Sorry, this here still equals 1. Equals 1. Let me just erase these guys here. And then I can simply bring 1 to the other side to make it 0, right? So this here would be 4m plus 12m plus 1. I'm going to subtract 1 from both sides. So negative 9 minus 1 here. So I have negative 9 minus 1, which will give me negative 10, right? Equals 0. Now what we can do is you can choose to do two approaches. You can either factor out the 2, because they're both even terms. So we can factor the 2 first, and then see if we can do factor by inspection. So let me do that. I can factor the 2 here. I'm left with 2m squared plus 6m minus 5 equals 0. And then I can bring 2 to the other side, so it cancels that out. So I have 2m squared plus 6m minus 5 equals 0. And then what I can do is I can do a factor by decomposition. Right? I have the product of 2 times negative 5 here. I will do this in blue. Is negative 10. Product here is that. Sum of it has to equal to 6. So I'm looking for 2 numbers that equal 6 here. So 10, 2 and 5, or 1 and 10. I don't think this is factorable. Let me just check. Negative 10 and 6. I don't think this is factorable here. So this is 2, 6, and negative 5. Oh no, this is factorable. Well, it's just I have to use quadratic formula in this case. Which means I could use quadratic formula to solve for my m value here. It's because this here is, I can't factor by decomposition, which means I have to factor by quadratic formula. Again, what I'm going to do is, I'm going to, for the sake of time, I'm going to, I will write out the formula here, b squared minus 4ac all over 2a, and I'm going to just use my calculator and cheat a little bit, and for the sake of time, I'll just plug it into a calculator. I'm sure by now, by grade 11, grade 12 math, you should know how to use the quadratic formula. So this here, x here would give me 0.68, and I also get a value of negative 3.67. So these two are my m values. Sorry, this here is the m value of these two functions here. And we were looking at extraneous solutions. So do I get an extraneous solution in this case? Could I actually is there discontinuity in terms of the top and the bottom? In this case, no, right? I couldn't cross anything out between the numerator and the denominator when we're doing the rational expression. So in this case, our answer here would be 0. So let's look at this function here. So they rewrote this in terms of, they moved the 1 actually to the other side first, and then they did denominator, which is fine. And then, let's see. Let's see here. Move on to the other side, and they use lowest common denominator. That's exactly what I did here. They've collected like terms. So you get negative 4m squared plus 9 at the very end here, because these guys cancel out. 4m squared and 4m squared cancel out. You're left with negative 4m squared, and then negative 9 plus 9. Or sorry, negative 6 positive 6 gives you negative 3 here. And then you can just simply just move this to the other side, and you rearrange and get a quadratic equation. So in terms of extraneous solutions, this here is not, this here you get extraneous, you get 2 solutions in this case. Because you have a 0.868 and negative 3.67. So in this case, we get 2 solutions. But when we talk about an extraneous solution, what is an extraneous solution? So remember, when we're solving for roots, or in this case, when we're solving for roots, we're looking at types of discontinuity, right, or a missing solution, right? So in this case, where we only know if a solution is extraneous if we could kind of cross it out, right, in terms of our if we could cross it out in terms of in a rational expression here. So in our when we talk about solutions here, negative 0.68 and negative 3.67 is indeed our solution for this problem, but it's not particularly an extraneous solution. I didn't cross anything out in terms of my rational expression. So this question is kind of misleading, and I think this this answer here says here, since this is a quadratic equation, and quadratic always has two solutions. That's not always correct, actually. A quadratic solution could have 0, 1, or 2 solutions. Hence, option C is the correct answer. So they thought option C was the correct answer. In this case, because the question is asking if how many extraneous solutions does the equation have below, this here is actually the wrong answer. So when we talk about extraneous solutions, require you to cancel out a term or an expression from the numerator and the denominator in a rational expression. Or let me do terms. Cancel out a term from the numerator and denominator in a rational expression. In this case, we did not have to do that. Indeed. So I'm going to say the solution, the question itself has two solutions, like you said. However, none of them are extraneous. So they did their math right. The math here is right, and I did the math here as well. But our math is right. But in terms of when we classify them as an extraneous solution, this is not an extraneous solution. This is simply just the root or the actual solution if we solved for m value here. So this solution I'm going to say is incorrect here. Okay, that took actually quite a bit. So let me move along here. This here is question 3. It says if h of x is the inverse of f of x, what is the value of h of f of x? So we're talking about this is a composite function now. So it says, let me rewrite this. If h of x is the inverse of f of x, what is h at f of x? So take a moment to think about this question. If h of x is the inverse of f of x, what is the value of h of f of x? So if you have h, so it's saying here, if h of x is the inverse of f of x, so let me rewrite this. So if h of x is the inverse of f of x, so this would be f of negative 1 of x, what is h of f of x? So in this case, if I use this substitution to simplify this, so this is here is 1, so therefore h of f of x would equal, so f of negative x of f of x, right? So that's what I'm doing here. But, so that's here. Again, if h of x is the inverse of f of x, what is h of f of x, right? So I'm doing this substitution here, because h of x is the inverse of f of x, right? So therefore, the composition function of h of f of x would equal, this would be the inverse of f of x. So in this case, it would just be x, right? That's it. Like the f of f. If you do the function and you do the inverse function, it just cancels out, right? You can think of it as, oh, if I had let's say 5 here, and you had 5, say 5 divided by 2. You had 5 divided by 2 as a term, and then you did the inverse operation for that, which is simply just 2 times 2, you just get 5, right? This 5 here is 0. You can think of it as the x, right? So if it's x divided by 2, I'm doing the inverse function, which is multiplied by 2, equals simply just x, right? So in this case, my equation here just equals x, right? That's all. These two kind of cancel out. This here equals x, right? So that's all I'm doing. The inverse of that, the inverse and the domain, again, the inverse function, the function itself and the inverse functions, when applied together, just cancels that function out. So you actually just get x here. So it says here, let a function of f(x) goes domain of range from range to domain. So they actually specify domain range, which is great. They did the exact same substitution as I did, where f minus x equals x. So given that, then we have h of f of x equals x here, right? That's good. Hence the value of h of f of x is just equal to x. This is a good solution. So this here is a great solution and analysis. Sweet. Okay. This here is number 4. So it says, how do I evaluate sine pi over 3 without using a calculator? How do I evaluate sine pi over 3 without a calculator? I'll just say with that because I'm not going to use a calculator for this. So how would I do that? So again, we're looking at this is a grade 11 classic question in trigonometry where we're talking about in terms of radians. When we're talking about trigonometry in terms of radians. So what we're going to have to do is we are going to have to kind of convert all of these guys into degrees, because that's what we're kind of familiar with, right? So let's do that. So let's convert this into degrees. So let's convert this into something that we know. So again, when we talk about sine pi over 3, pi here equals 180, right? So we're talking about this is sine pi, which equals 180 degrees. So wait, let me just write this down. So if pi equals 180 degrees, then sine pi over 3 equals sine, this is 180 degrees divided by 3 here, which equals sine 60, right? Sine 60. Okay, so if we have sine 60, then what we have is this is testing us the knowledge of our special triangles, right? So for example, if we had something like this, where let's see, we have something like if you remember from our special triangles, what this would give us would be, we would have to draw out a triangle that looks something like this, and I'll show you here. We have to draw a right triangle, and this angle here is a 60-degree angle. This here is a 30-degree angle. And what that would give us in terms of lengths would this one would be a 1, this here is a 2, and this here is a √3, right? So that is my special triangle. Remember, this here is a special triangle. We have to learn two special triangles in grade 11 or in algebra 1. We have the other one here, which is simply 45 degrees here and 45 degrees here, right? And this is a 1, 1, and √2 kind of triangle here. So these two are special triangles. These are very, very important. So I'm going to start them. These are very, very important ones to know because you're going to have to find the exact value of a lot of these guys here. Okay, so in doing that, where you're going to use the first special triangle, right? Because I have 60 degrees. This here is the only triangle with 60 degrees. I'm finding the sine of that, right? Sine 60. What's sine 60 here? This is the opposite over the hypotenuse. So the opposite here is √3. Let me do this in blue. So sine 60 would equal the opposite over hypotenuse, right? Which is here. The opposite of 60 degrees here is the √3. And then the hypotenuse here is 2, right? This here is the hypotenuse, which is 2. Therefore, sine, and I can convert this back to radians, sine pi over 3 equals √3 over 2. So this here is my exact value of sine pi over 3. So let's see how they did here. Let's see what they did with this here. So it says, how do you calculate sine pi over 3? Sine pi over 3. Okay, sine pi over 3 equals 180 divided by 3. That's good. Sine 180 degrees divided by is sine 135. This here is incorrect here. Sine 180 divided by 3 here is sine 60, not 135. So they actually did the question wrong here. This step is wrong. And then when you have sine 60 equals sine 90 minus 30, okay, they're using an identity to help solve for sine 135 in this case. So this here is actually a wrong solution because of this step here. Sine 135 does not equal this. Solution is incorrect because of this statement. I'm going to say here, so sine 180 divided by 3 equals sine 60, not sine 135. Therefore, the correct solution is sine pi over 3 equals, this would be √3, so square root of 3 over 2. So here, therefore that's the correct solution. So again, this solution here is incorrect because I have my special triangles here. Okay, that was question 4. Let's do question 5. So it says here a sequence is defined by the recursive formula f of n plus 1 equals f of n minus 2 if f of 1 equals 18. What is f of 5? So let's hear this question 5, right? So I have a recursive formula. This is f of n plus 1 equals, f of n plus 1 equals, this is f at n minus 2. And if we're saying here, f at 1 is 18, what is f at 5, right? If f at 1, so saying if f at 1 equals 18, then what is f at 5? So let me plug in f of 1 here, and let's see how it satisfies this equation here. So f at 1 means that n would equal 1, right? So if n equals 1, then therefore, I'll do this in blue because it's not a solution yet. If f at 1 here, n here has to equal 0, right? Because this entire thing has to equal 1, right? Therefore, the only logical thing here, n has to equal 0, right? Equals, and f at n would be f at 0 minus 2. This here would equal 18, right? This entire thing equals 18. So what I can do is I can actually solve for f at what f at 0 is naturally, right? Because if I know f at 0 minus 2 equals 18, then what I can do is I can do f at 0 minus 2 equals 18. I can move 2 to the other side, so I have f at 0 would equal 20, right? So that's going to be my my first kind of giveaway in this problem here. F of 1 equals 18. So what I can do then, what I can do now is I can solve for f at 2, right? Because if I know f at 0 is 20, so I'm going to write this down. F at 0 is 20, and I know f of 1 is 18. Let me solve for f at 2, right? So let me erase this. Let's solve for f at 2. And you're going to see a pattern soon. So this is f here because it's a recursive formula, right? So I'm going to say f at 2. I want to plug in f equals at 2 would equal, this is f at 2 minus 2, right? So wait, hold up. Give me a second, sorry. So f at 2 would equal, let's see, if n here equals, so let me do f, so n here equaled 0 in this case. N at 1 would equal, or f at 1 would equal 18. Let me try f at, if n equals 1 here. So if n equals 1, you get something like this. So f at 2 would equal f at 1, which is 18 minus 2. So f at 2 would equal 16. So let me write down that f at 2 would equal 16 here. So it's going to see some type of pattern, right? 20, 18, 16. The next one's probably going to be 14, right? It's decreasing by 2, right? So that's kind of our recursive formula here. So I'm going to verify that by solving for 3, 4, and 5 as well. So let me verify that for you. And you're going to realize that it's going to be a pattern here. So I'll solve for one more. So if I found that, if I found f2, let's do f at 3. So f at 3 would mean that n here would have to equal 2, right? So it would equal f at 2 minus 2. So f at 3 equals, f of 2 is 16 as depicted here, minus 2, f at 3 equals 14, right? So I have f at 3 equals 14. Therefore, if I kept doing this thing here, f of 5 would equal, again, f of 4 would be 12, and the f of 5 would be 10, right? It's simply just decreasing by 2, right? So it's defined by this this here. This is the recursive formula, right? If I have n plus 1 here, the next n value would give me whatever the previous one here is subtracted by 2, right? So whatever this here is subtracted by 2, this here is 2, this is subtracted by 2, this is subtracted by 2, and this is subtracted by 2. So this, therefore, f at 5 equals 10. Okay, so let's solve this. Let's look at this problem here. So they put n equals 1. They solved for it. To f at 2 is 16. That's good. F at 3 is 14. F at 4 is 12. F at 5 here is 10. So they actually just subbed in all the values, and then they plugged it in. So this is a good solution. Good solution, and step by step. I wish they included what defines a recursive formula, and what a recursive formula here is the next function here depends on the value it was previously. So f at 0 or f at 1 depends on f at 0, f of 2 depends on f of 1, f of 3 depends on f of 2, right? It depends on the f of the next number, so and f of n plus 1 depends on the previous n value, and we're going to subtract that by 2 here in this case. So I wish there was a definition or explanation of what a recursive formula was. Next, f at n value depends on the previous f of n value minus 2. Yeah, that's good. Okay, sweet. So solution here is correct. Either way, the solution is correct here. Okay, let's look at number 6. So it says use synthetic division to solve for that thing. So which is x to the power 4 minus 1 divided by x to the minus 1. So what are we doing to solve this? So it says use synthetic division. So when we talk about synthetic division, we can use kind of two approaches to synthetic division. We can either use synthetic or we can use long division. It doesn't really matter which one you use. Both of them will get you the same answer. So take a moment to think about this question. So yeah, take a moment to think about this problem. And we're going to kind of take it up as we go here. So in this case, this is synthetic division. So again, this is relating to, we're talking about simplifying our rational expressions here. We can talk about finding maybe we could get something like a cubic function here. We're basically just simplifying our polynomial here in this case. So it says use synthetic division to solve for this problem here. So we're given this, so we have to use a synthetic division. So how I would do it is I would do like a little inverse kind of division here. And then in this here, I would put whatever the coefficients of this here is, right? So the divisor would be simply just 1 because I have 1x, and then the dividend or the thing that's inside the bracket would be I would have 1 for the x to the power 4, and then I have to go down by degree. So for the x to the power 3, I have obviously a 0. X to the power of 2 is a 0 as well. X to the power of 1 is also 0, and you have a negative 1, right? So this here is my start of my synthetic division, right? So these are all placeholders, right? Because this here represents my x. This here, x to the power 4, 3, 2, 1, and this is your constant value here. So so I set it up. This is good. So what we're going to do is we're going to take the first number inside. It represents the leading coefficient. We're going to carry it down, right? So in this case, let me just extend here. Let me just extend this guy. This is a 1. Just extend this. Okay. So what I'm going to do is I'm going to bring the 1 down. 1 like that. And then after I bring it down, I'm going to multiply it by the divisor here. So 1 times 1 obviously equals 1, right? So this here would equal a 1 here. And my answer will go into this space, so the next space here. So we do the exact same thing, and we're going to, so after that, after we multiply the divisor by whatever this number brought down was, we're going to take, we're going to add this next column here. So 0 plus 1 here is obviously 1, which means I'm going to get a value of 1 here. So I'm bringing this 0 down. 0 plus 1 here is 1. So that's great. And then what we're going to do is we're going to do the exact same thing. So 1 times 1 here is, again, it's a 1. So I have another 1 here. Bring the 0 down. 0 plus 1 here is 1 again. And then I'm going to have to, I get another 1 here. 0 plus 1 is 1. 1 times 1 here is 1. I bring this down. Negative 1 plus 1 here is a 0, right? So I get a 0 here in this case. So what am I left with? So I'm left with all the leading coefficients of of the answer, right? So this here would be a, so this here I have this here is a 0, this here is x squared, x cubed and x to the power of 4, right? So in this case, I would get something like this. I would get x to the power of 3, x to the power of 2, and an x value here. So let's check what they did here. So they did kind of the same thing in terms of the synthetic division method. They wrote all their values like this, like in terms of a square bracket, which is totally fine. I did it in terms of this like inverse division. It's super fine as well. They got 1, 1, 1, 1, 0, which is exactly what I got. So which means therefore the quotient would be x squared, x squared, x cubed, x squared, x, and x plus 1 here, right? Because the entire thing here now shifts, right? Because this here is now, so instead of the x to the power 4 being here, this is now x to the power of 3, right? Because I divided 1x by x to the power 4. So this here, this new solution here is our leading coefficient of our answers, right? So our answers here, this is x to the power 3, x to the power 2, x, and whatever our constant is. So therefore, our answer to this problem would be, so x to the power 4 minus 1 divided by x minus 1, right? Let me just double check that. Yep. So this would equal, I would have x to the power 3, or I would have 1 times x to the power 3 plus 1 to the power of x plus 2 plus 1 to the power of x plus 1, right? Therefore, it's simply x cubed plus x squared plus x plus 1. And that's going to be my answer for this problem here. So it's exactly the same as what they got. They did their long division in a different format as I did, but we still got, the important thing was we got the latent coefficients correct, right? This here is our correct answer, and that's what they got in the bottom row here. So this here solution is a great solution. So perfect solution and step-by-step analysis here. So you could use something called synthetic division. You could use something called a long division. And let me just show you that real quick before we move on. I'll just do like the first couple steps, and then you can kind of get the idea. So I would put x minus 1 over here, and I would divide it by x to the power 4 plus x 0 x cubed plus 0 x squared plus 0, or no, plus x minus 1. And what I would do is you have to go kind of back to grade 6 or something like that when we learn about long division. So we take the first two terms here, x minus 1 and x to the power 4. What do I need to multiply to x to the 4? I need x cubed, right? And then what you can do is x cubed times negative 1 here is negative x cubed. And this here is obviously x to the 4. And then you're going to subtract both of these sides. So I have a 0 here. And this here would be plus 1, right? 0 plus minus x would be 1x cubed. And then which means, and they do the exact same thing, right? So you have to, what value of this times x minus 1 will give me x cubed? Again, x squared would be my next value here. And then I would go so on and so forth. And you realize you get the exact same thing as if you were to do synthetic division. So another way of approaching this, again, it's up to you in terms of how you approach this question. Synthetic or long division. In this case, they asked for synthetic division, so we have to use synthetic division in terms of this way here. But long division does tend to be a bit harder just because it's a longer step, whereas synthetic division is a bit more accessible. It's a bit easier because we're just bringing down and multiplying, right? Whereas this one is a bit harder to visualize. So we say solution is correct. Okay, let's do this function here. So this is number 7 now. Doing okay for time, I think. Piecewise functions, I have f of x equals, this is the piecewise function of x squared minus 4x minus 5, where x is less than 5, and then of x plus 3, and x is greater than 5. Okay. So if I want to plot this function here, what I'm going to have to do is I'm going to have to draw a graph here. Or it's asking what graph represents this piecewise function, and then they give you like 4 different graphs, right? So that's fine. So let me sketch out my own graph to figure out what the solution here is. Again, this is just a sketch, right? I'm not very, very good at sketches here. I'm going to say this here is 5. Because that's my point of interest here, right? At 5, I have x is less than 5 and x is greater than 5. So therefore, at 5, I'm actually going to get a removable discontinuity, or I'm going to get something, just because if I evaluate the function at x equals 5, I'm not going to get no solution, right? I'm going to get no, it does not exist. So I will have a little hole or removable discontinuity at that kind of point here. So let's draw let's draw this over here. So it's x squared minus 4x minus 5, right? And that x is less than 5. So let's evaluate this point here. So what would the point be at x equals 5 if it were to equal 5? So I would sub in x to the power of x equals 5 for the first equation. So I'll do it in blue for the first equation here. So this here, I would sub in f at 5, right? So f at 5 would equal, this would be 5 squared minus 4 times 5 minus 5. 5 squared is 25 minus 20 minus 5, which equals 0, right? So in this case, this here equals 0. So I have a hole at 0. And I'm going to do my function in blue because I started out in blue anyways. So that's my point for this function here. And let's solve for this other one here. This will be in red. This is for if x is greater than 5, it's x plus 3. So I'm going to say if f of 5 equals x plus 3 here, which means I still have 5 plus 3, which equals 8, right? So then my other point here is also a hole, is I'm going to say that x here equals 8. So I'm going to say maybe 8 is up here, and I have another hole that exists here as well. I'm gonna let's plot my red function here first. It's an easier function to plot just because I know it's a linear function here. So the slope is here is simply just 1, right? So my next point, for example, would be the rise and run are both 1, the value of 1, right? So my next value would be 6 here, and then I would have 9. So I would get something like this. Or sorry, I was gonna do that in red for you. Red here, and for the sake of space here, I'm just going to plug in 1 point, right? So again, I have a point here, so this is going to go this way and extend this way. And then for my quadratic, I'm going to do in blue. Again, I have here, this is x equals 0, and again, as you can see, my parabola is opening downwards, right? So this here would be the vertex of my parabola. So it's going to be it's going to be a decreasing function. It's going to hit 0. This will be my vertex, right? Because I'm hitting I don't go below 0 here. So I'm going to prove that. I'm going to sub maybe x equals 4, for example, and I'll show you what the points are here. So let's see 4. So if I did f at 4 of this function, so I'm going to do this in blue again. So f at 4 of this x squared minus 4x minus 5, I simply just plug in 4 squared minus 4 times 4 minus 5 here. This is 20 minus 16 minus 5, which equals 4 minus 5, which equals -1, right? So here's -1. So let's see. So it's actually not my vertex in this case. Sorry about that. I think I said that incorrectly. But this here is a point -1 and 4, right? So this here would be maybe like here. So here's in blue, so maybe something like this here. And what I can do is I can actually solve for my my y-intercept of this function, because I know the parabola is going to hit my y-intercept, right? So I can sub in x equals 0 to solve for my y-intercept. So let me just solve this last part here. So I can say if I can sub in f at 0 equals, this would be 0 squared minus 4 times 0 minus 5. This here is 0, this is 0. I'm left with positive 5, right? Yes, or no, sorry, I'm left with -5 here. So this here is just -5, which means my value would be something like here. Wait, hold up. I don't think I did that correctly. Minus, I have 0 squared. Sorry, let me just take out my calculator for a sec. I plugged in a 0 here, right? So this is 0 squared minus, this is 4 times 0 minus 5. Give me positive 5. Sorry, I messed up here. This is positive 5, which makes more sense, because this here minus gives you positive. Sorry. So this here is a positive 5, which means I have a point here. This is, let's say maybe here is 5. So I can safely say that this parabola will go something like this. It would go at 5. I would get some vertex here, and then it would cross this point and move upward like that. So that's here. This here is my function for my piecewise function. And all I'm going to have to do is I'm going to define this here. The first one's not correct. There's a point here. There's 2 points here. It's either it definitely only has to be this function here. Let me just check. That's not correct. The y-intercept is, oh, sorry, the y-intercept is -5 here, right? Sorry, just give me a second. This is, yeah, 0 squared minus 4 times 0 minus 5, right? So, oh, this is -5. Oh my gosh. So I didn't do my math correct. Oh, my bad. So this here is -5. I don't know why I doubted my math. I always do that. That's my fault, sorry. So this here, here is -5. Which means my parabola looks something like, looks basically what this third function here is. So it basically loops up, it basically goes down and loops up at some point and then comes back up like this to that point. Sorry, not to this point, to this point here. So it's very, very similar to what I have here. So, and because of the shape of my graph, it's not that accurate, but I'm trying my best. Basically it loops up like that. I needed to hit that point, so sorry. Something like that. It looks like a V, but it's totally fine. Basically the answer, because I know they're both removable discontinuities, I know it's actually it's answer C here. So this here is answer C. And the reason why you can actually arrive to this answer by you don't even have to use algebra based on the solutions here, just because I know that there's a removable discontinuity at 5, and this here is a jump discontinuity. This here does not have a discontinuity. This here is another jump. Actually, this is not a function here. F5 has 2 defined values, which means this is not a function, and this here is another jump. So jump discontinuity, not a function. This here is indeed my correct answer because I have 2 holes, and then this here is another jump discontinuity. So I don't even have to use the algebra, and I can simply just say that C here is my correct answer. So I'm just going to, again, this probably will be my last question, I think, it's 10:57. But it's saying here, the first equation is parabolic, because it's a quadratic equation. The second is a linear, as it's a linear equation. Does that make sense here? The first one here is, no, they're all parabolic. Second is linear, takes value x is greater than 5. Okay, that's good. Both breakages is shown by the white dot, as both points or any of the points are not equal to 5. So this here is a correct solution, but I really don't like the reasoning. And the reason why, but decent reasoning. And the reason why is that we know that there is a should have said there is a discontinuity at x equals 5 because both functions do not include x equals 5. It's only if it was less than or greater than x equals 5. Because I don't, basically if you look back to my function here, f of x is x squared minus 4x minus 5 if x is less than 5, and if x plus p is greater, for x is greater than 5, right? But I don't have a condition that satisfies. What about x equals 5? Like, what about at x equals 5? Do I have a function here? In this case, the top function does not exist for this one, and the bottom one isn't either. There's no greater than or equal to or less than or equal to, right? So there's actually no function that defines at x equals 5. So therefore, where C is the only correct answer, because x equals 5 is undefined. So say solution here is correct. So this here is my final answer for today. Again, I only got through 7 problems. That's totally fine. It did take a while to kind of go through these problems because, again, these are much more like senior math level questions. Right? We're heading to pre-calculus. This is grade 11, grade 12, right? Math that we're talking about. So ideally, the problems are getting harder and harder and harder. So it does take a bit of time for me to go through this problem with you as well. So therefore, solution is correct. and we are good for that. So again, thank you for watching this video. If you liked this video, again, definitely subscribe to the OneClass channel to keep up with the streams. And I'll be streaming Monday to Friday, mostly with math and chemistry. So if you liked what I taught today, please feel free to tune in those streams or watch the videos that are going to be reposted. But yeah, as always, thank you for watching. Stay safe, stay healthy, and have a great day.